This video is on the strengths of acids and bases. We know that an acid wants to donate or does donate a proton, and a proton in this case would be an H. And we know that a base wants to accept a proton or accept an H from the acid. So how do we know how strong these acids or bases are? The strength of both of them, the acid or the base, depends on the extent to which they donate or accept the H to or from water. So a strong acid dissociates completely in water. So there are 6 strong acids, which I will show you on one of the next couple of slides. But full dissociation means that there will be no reverse reaction that will happen. Here's an example of a full dissociation equation for hydrochloric acid. Hydrochloric acid is one of the 6 strong acids. So you can see here that this arrow is only going in the forward direction. There is nothing happening in the reverse direction. And what happens, our acid here is made up of H's and Cl ions. It completely dissociates into the Cl ions, and the H is given to the water where we have the H3O plus ion. So that is a full dissociation. That will happen with these 6 acids. These are the 6 strong acids. You want to remember these. So we have nitric acid, we have sulfuric acid, we have perchloric acid, we have hydrochloric acid, we have hydrobromic acid, and hydroiodic acid. The conjugate base column here, it's whatever the ion is once the acid donates the H. So in this case, it would be NO3 minus 1, HSO4 minus 1, ClO4 minus 1, Cl minus 1, Br minus 1, and I minus 1. If an acid has more than 2 H's, like sulfuric acid for example, that would have 2 different dissociation steps that go with it. This is called a diprotic acid. Di because there are 2 H's. If you have an acid like phosphoric acid, for example, that has 3, that is called a triprotic acid. Strong bases, just like strong acids, completely dissociate in solution. So instead of creating that hydronium ion like acids, you'll have your hydroxide ion and then whatever cation was involved with the base originally. A lot of your strong bases will come from group 1 and 2 on the periodic table. Strong acids and bases are both strong electrolytes. So they will conduct electricity. Here are common strong bases. So you'll notice the cations for them are from group 1 and group 2 in the periodic table. So which of the following compounds is a strong acid? So this is just a memorize thing. The only strong acid there is sulfuric acid, H2SO4. So what are these? These are called weak acids. Strong bases. We have our calcium hydroxide, sodium hydroxide, and our barium hydroxide. Again, these would just be weak bases. So what is a weak acid and a weak base? It has to do with the dissociation. So strong acids and bases dissociate completely. Weak acids and bases are characterized by little dissociation. So they produce few ions and they are weak electrolytes. Important, the reaction is reversible. So you can see in this equation here, this double arrow. That means the forward reaction is happening at the same rate as the reverse reaction. So these ions, they are dissociating over here, but then they're unhappy and they're going back to form the original acid and base. Weak acids and weak bases are weak electrolytes, as you may imagine. So again, just looking at conductivity here, a strong electrolyte, we have the light bulb fully on. A weak electrolyte, it is not fully on. And then a non-electrolyte, anything molecular, it would not conduct electricity. So your electrolytes come from your ionic substances. Your non-electrolytes come from your molecular substances. There are examples here of weak acids, inorganic acids, organic, but really anything that is not a strong acid is a weak acid. So you have 6 strong acids, everything else, all the other acids are weak. And same thing with bases. If it's not a strong base, it is a weak base. So just an important one that I mentioned in a previous video, NH3, it's kind of a hidden base. There's no hydroxide ion, but you just have to know that that is a weak base. Again, look at your double arrow there for equilibrium. So here we're saying if they're strong or weak. If you memorize the 6 strong, the rest are weak. This shouldn't be too difficult. So that is my strong one. That's nitric acid, hydrochloric acid, and then that's acetic, vinegar, and hydrofluoric. Something we talked about back in chapter 6 was Le Chatelier's principle. And this says that the reaction shifts in the direction that counteracts a disturbance. So we will get a shift to the right, aka the forward reaction, if there is a disturbance, and this could be from the left side or the right side that the disturbance takes place. It could be adding something or removing something. And then reverse reaction, same thing. It could go left depending what we do to the reaction. So here it says ammonia. We want to write the equilibrium reaction for ammonia in aqueous solution. So now would be a good time to pause the video and try these 3 questions here. So here is the equilibrium reaction for ammonia. Let's concentrate on the top line first. So we have our base, and it's an aqueous solution, so there's our water. And I'm going to label these guys acid and base. My acid wants to give away my H, so this H is going here. That becomes my conjugate base. He becomes my conjugate acid. Notice the sign changes that occurred. And that's the equilibrium reaction. Make sure you have double arrows there. Why? Because NH3 is a weak base. So there needs to be double arrows. And then below that, you can see just the Lewis structures drawn for all of them. The second question says that if additional hydroxide ions are added, will it shift left or right? So let's look where the hydroxide ions are. The hydroxide ions are here. So if we add more of them, that reaction is going to want to produce more water and ammonia. So this would want to shift to the left. If we get more of this, we have more reactants to work with. It's going to want to shift this way to produce more of these guys. Another way of thinking about that, if we have more of this, to balance it, we need more of this. So we need to produce more of this, so we need to shift left to the reverse reaction. And the last part, C, it says, if some ammonia molecules are removed from the solution, will the reaction shift to the left or right? So find ammonia, so that's this guy. If we are removing that, we need to get more of it to replace it. So we need to produce more ammonia because we got rid of it. So we need to still shift to the left. The reverse reaction needs to occur.